Okay, 8.1 is on arc length. Instead of computing or finding the area under the curve, we are going to compute the length of the curve, let's say from A to B. Let's say this function y equals to fx, and we are interested in finding the length of the curve. The way it will be done is as the following. We will partition this interval A to B into a lot of smaller sub-intervals. Okay, let me grab this section here. Okay, let me grab that section and enlarge it. And you will see something similar to this. Now, once you super zoom that curve will eventually look like a line segment. Now, we are interested in finding the length of this very small segment here. We will do it in the following way. We will use Pythagorean theorem, in which this will be our dx, this will be our dy, and we will call this ds. Okay, and ds squared by Pythagorean theorem, ds squared is equal to dx being squared plus dy being squared. Therefore, ds is, it is a differential form. That's why I use d in front of that. That's the square root of dx squared plus dy squared. Now that's for that one section. The thing is, along this curve, there are a lot of such sections. There are a lot of such sections that I will add. Okay, can you imagine, right? And it has to be super small though. It has to be very, very small. Okay, so basically then you will see the arc length that we are looking for is equals to the summation of such ds, where that ds supposed to be super small. Okay, maybe I look back a little bit. Instead of using d, let's use sigma for now. Let's use sigma for now. So I use sigma x, that's the difference of x, and then difference of y, and this is the difference of the hypotenuse. And then what I did earlier is not wrong. It's just like I tried to explain that from the limit point of view. So the difference of x being squared, difference of s being squared equals to the difference of x being squared plus difference of y being squared. Okay, so the difference of s is square root of difference of x squared plus the difference of y squared. Okay, so to find the arc length, we are basically adding all those difference of s, but under the condition of limit, this becomes, under the condition of limit, this guy here becomes integral.
So that yellow part which you highlighted is the change in S?
Is the one here?
Yeah.
Yeah, basically I supersum whatever I have there. Looks like this.
Okay.
Okay, we can call that delta S. We can also call that ds. Yeah, depends on do you want to apply the limit or not. Once we apply the limit, then limit sum becomes integral, while the delta S becomes ds. Okay, so in other words, if we look back to this equation here, if I make the difference of S a lot smaller, then this becomes dx squared plus dy squared. In limit condition. Okay. That's why then arc length usually also denoted as S equals to integral of ds, where ds is equals to square root of dx being squared plus dy being squared. Okay, and it is actually that notation actually in line with the notation we have before. Just to remind you that what is integral of dx? X plus constant, is that right? Are you with me? So integral of ds is s plus constant, right? But we ignore the constant for now. I usually joke this way: the sum of small dangers is equals to anger plus constant. And the integral of small devil is equal to evil plus constant. Of course, the last two just notation play is not real. Okay, it's not real. Now, let's come back here. From our sketch here, from our graph here. So suppose I want to find the length of the curve from A to B, from x equals to A to x equals to B, then my integral will be, let y equals to fx, then the length from x equals to A to x equals to B is given by s equals to integral from x equals to A to x equals to B of that ds. Is it right? Now the thing is we have two variables of integration right now, dx and dy, while the interval is the interval in x. Okay, now then there's a violation there. We need to fix something. What thing to fix? If the limits of integration in terms of x, then the variable of integration should be dx. Are you with me? That's why I keep on penalizing you in your tests, in your quiz, when you show your work, I penalize you. Once you do substitution, if once this is in U, for example, then the limits of integration has to be in U also. Okay, you cannot say, oh, this is in X and then this is in U. No, it doesn't make sense. Okay, even this notation, that the one I show you right now, is already a violation because the limit of integration in terms of X, but the variable of integration, you have dx and dy, while you have only one integral sign. So something is very terrible there. Something is very terrible there. Now, how do I fix it though? How will I fix this? I will get dx outside. Okay, I will factor dx from here. Okay, I will factor dx from there. It is by doing the following. That's integral from a to b. I factor square root of dx squared out. You see what I mean? Therefore, now I get the arc length for a function y equals to fx from x equals to a to x equals to b, square root of 1 plus dy dx being squared dx. Okay, let me draw the situation again. Okay, where the function is given as y equals to fx, right? And then the interval is on interval of x from a to b. Then we will use this formula. Suppose I change the issue. Suppose we have x as a function of y instead. X as a function of y instead. So our curve may look like this, where this is C and this is D. The y is a function of x. Oh, I'm sorry, x is a function of y. Okay, so our arc length will then be integral from C to D. Don't forget, the C and D is on the y-axis. Okay, originally it's supposed to be square root of dx being squared plus dy being squared, right? Suppose originally that's what it looks like. Now the thing is, because the variable of integration, limits of integration in terms of y, then the guy here is supposed to be dy, right? Now, because I need to factor dy out, it means the guy inside the house should be divided by dy squared under square root. This then becomes 1, while this then becomes dx dy being squared. Okay, we are done for this section. Problems? Suppose, for example, I do number, what is good? Let's say I do number 8. Find the exact length of the curve. Find the exact length of the curve. Find the exact, so don't do rounding. They don't need to say the exact length, they just need to say the length, and then you still don't do round. If you need to give me decimal, write the exact form first before you give me the approximated decimal of the curve y squared equals to 4 times x plus 4q, where the x between 0 to 2 and the y to be positive. Now they tell us the interval in x. So what I need to find out is, I need to find this. I need to find 1 plus dy dx squared. I need to find that. Okay, but for us to find that, we need to first find dy dx. Is it right? Now to find dy dx, let's see what is y first. Y will be the square root, and we take the positive branch. Okay, we take the positive branch because of this. I take positive branch, the square root, and then I do square root here. That will be x plus 4 to the power of 3 halves. Then I do the derivative. That will be 3 times x plus 4 to the power of 1 half. Then if I square it, I get 9 times x plus 4, which is 9x plus 36. So 1 plus dy dx being squared under square root will be square root of 9x plus 36 plus 1. Now set it up properly first. Okay, set it up. Don't rush when it comes to setting up. Please don't rush, because anything wrong you do here, for the rest of the question, you will be just wasting your time. Okay, if you can't even set it up right, forget the rest. Okay, no wonder then you have a very terrible integral to work with, because you already have some miscomputation in between and you end up wasting your time there. Not a good idea. Okay, so yeah, y37, because I add 1. Is it okay? I add 1. Well, you can just slow down if you want, but eventually that's what you will get. Now then I go on with the second part, the integral. So the arc length is equals to integral from 0 to 2 square root of 9x plus 37 dx. That's what you need to compute. Okay, now from here u equals to 9x plus 37, so du is 9 dx. u0 is 37. u2 plus 18 is 45. Now then my integral now becomes integral from 37 to 45 of u to the power of 1/2 times du over 9. That's 1 over 9 times 2 u to the power of 3/2 of 37 to 45.
Shouldn't U2 be 55?
Oh yeah, that's right. Not 45. 55. Then this will be 2 over 7. Now u to the power of 3 half is basically u times u to the power of 1 half. So this will be 55 square root of 55 minus 37 square root of 37. Okay, maybe I write it here. U to the power of 3 half is u times u to the power of 1 half, which is u square root of u. Okay, of course, if you can simplify further, you should do that. But I think that's the furthest we can go without being using decimal. Furthermore, how about number 10? Number 10, we have x as a function of y. X is y to the 4th over 8 plus 1 over 4 y squared. The y is from between 1 and 2. So find the arc length. If I sketch that, let's say this is the curve, right? Find the arc length from y equals to 1 to y equals to 2. Set it up first. Don't rush with your setup though. Trust me, in your test, when I grade it, I have students using this substitution here. 1 minus x squared equals to u. And that students say that x squared equals to u minus 1. I don't think so. I don't think so. That's not true. That's not true. And in fact, because of this mistake, because exactly for this mistake, I noticed two students actually working together. They make exactly the same mistakes on two problems on the same page. And that's how I identify these two students cheating from each other in the test. When I look further into their detail of work, I found out that not only they make this same mistake, they copy basically, I can tell who copies from who, but doesn't matter. That's academic dishonesty. And I just penalize all the points, if not all, most of the points or all the points for, like, they show the work exactly the same way. Dude, you are in calculus 2. Whatever you turn in is recorded. Okay, and I can show that to the dean, I can show that to the department chair, and of course, I teach statistical, so I can argue the probability that two people making exactly the same mistake line by line, and they happen to work independently, is near 0, if not 0. The probability is so small such that it is more likely I win a jackpot 4 times this week. This same week, 4 times. Mega Million, Super Lotto, Powerball. Okay, and if you happen to listen to this, I somehow suggest you to drop the class. I know there's a chance that you do better in your test 2, 3, 4 and your final without cheating. I know. But the fact that in my test 1, you already start cheating means you are very far behind. Not a good idea. Not a good idea. When do we get the result? Tomorrow morning. The person who make this kind of cheating actually slowed me down such that I have to look back further. I was just like, man, what is this person doing? You know, okay. You're in calculus 2. Even when you need to cheat, do it in a smart way. Okay. If that person use you, you don't use you. The sad thing is, like, you just copy that without thinking, and you make exactly the same mistake like this. You show this to my pre-algebra student, they will be laughing at you. Okay. I don't blame the person who make this mistake first. I blame the person who cheat from the person who make this mistake and just copy that down instead of fixing that person's mistake. It's like you work together to make more mistakes. What kind of working together is that? Oh, come on. Well, anyway, because this is the interval in y, so I will have dy later on. The integral will be in terms of y, right? And then the square root, therefore, will be dx over dy squared plus 1. Okay, that's what we need to do. With that said, then, okay, now I know what I need to do. I need to find, first step, I need to find dx dy. Do the derivative of x respect to y. That will be 4y cubed over 8 plus actually becomes minus because this is y to the 4th over 8. This is y to the negative 2 over 4. Right? When I do the derivative, it becomes negative 2y to the negative 3 over 4. Simplify to make life easier. That's why you call that simplify your life, right? Then from there, we get, when we square it, I wonder what happens if we square that polynomial. So that becomes 1/4 outside, right? This is y to the negative 3. Okay, and then I get y to the negative 3, y to the third minus y to the negative 3 being squared. That is equals to 1/4 y to the 6 minus 2 plus y to the negative 6. Now let's add 1. If I add 1, so dx dy being squared plus 1 equals to 1/4 y to the 6 minus 2 plus y to the negative 6, all of them plus 1. But that's the same to add 4 over 4. Okay, that gives us, I factor the 1/4, I keep the 1/4 outside. Now inside, it becomes y to the 6 plus 2 plus y to the 6, which is 1/4 y cubed plus y to the negative 3 squared. Now the square root of that ugly guy, the square root of that dx dy squared plus 1 is therefore 1/2 times y cubed plus y to the negative 3. Okay, but please be a bit careful. Please be a bit careful here, because the following: the square root of anything squared is equal to the absolute of x, supposed to be. Okay? Square root of anything squared is equals to the absolute of that thing. It is incorrect to say equals to x. It is actually not correct. Now, in this case, I say you need to be careful because this is true. You can omit the absolute value only when the y is positive. Only when the y is positive. Now, if you look into the domain of the integration, the y is from 1 to 2, right? That's why then you don't need to use absolute value. But imagine if I kind of like try to trick you and then I say that the y is from negative 2 to negative 1, you know, right? Okay, then it won't be that simple anymore. Okay, now that's the integrand. Now we go to the integral. So the arc length is now integral from 1 to 2 of 1/2. Is it 1/2? Yeah, 1/2 y cubed plus y to the negative 3 dy. One to two. So when y equals to 2, that will be 4 here minus 1/8 minus when y equals to 1. Okay, and from there just compute it as usual. It's 31/8 minus negative 1/4. That's 1/2 times 33/8. That's 33/16. So you see that from here, you see that I spend actually more time in doing the setup correctly and then compared to doing the integration. Okay, so with this, I hope I show you enough that be patient when you do the setup. Okay, please be patient with you when you do the setup. Once you don't set it up correctly, the integral here will not be working, will not be easy to integrate. Okay, the problems in our textbook was carefully chosen such that if you set it up right, the integral becomes easy. Okay. Now let me ask you to try. Let me ask you to try question number 18. Find the arc length for y equals to 1 minus e to the negative x for x between 0 to 2. Let me give you maybe 1, 2, 3, 4, 5, 6 minutes to set it up. Let's start. The interval is from 0 to 2. Let me try this. So dy x equals to e to the negative x. dy dx being squared is e to the negative 2x. Oh. Dy dx squared plus 1 under square root is square root of 1 plus e to the negative 2x. So the arc length will be integral from 0 to 2 of square root of 1 plus e to the negative 2x dx. I wonder if we can integrate that. Do you know how to integrate that? Seems like we need to be a bit more creative here. Okay, let me try to work it out. Let me try to work it out. the first option is I will go on with this integral, but I will do the following. This is 1 of plus 1 over e to the 2x dx, which then I plan to do the LCD thingy. Okay, so I have square root of e to the 2x plus 1 over e to the x dx. What do you think? I wonder if it helps. I don't know. But then if my u equals to, how do I get e to the x under square root, right? Because this is square root of e to the 2x plus 1 over e to the 2x inside the square root. Is it okay? Don't worry if you do it wrong right now. That's okay. Don't worry about it. As long as it's not in the test, right? Okay. Well, anyway, if u is my e to the x, then my du will be e to the x dx. I wonder how much it will help. So u0 is 1, u2 will be e squared. So my integral now becomes integral from 1 to e squared, square root of u squared plus 1 over u times my dx is du over u. So this is integral from 1 to e squared, square root of u squared plus 1 over squared du. I think I will do substitution. Or do you want to use sine, tangent, stuff like that? You can if you want to. Okay, from here, so there are two ways. I think I prefer the first way. So call this 1a. This is 1, right? This is method 1. Somewhere in between, we have two ways. 1a, later on I will do 1b. Okay, the first one, 1a, I will use w equals to u squared plus 1. So u squared minus 1. Oh, you know what? Let me make it w squared instead. So use w squared minus 1 equals to u squared. And the 2w dw equals to 2u du. I wonder how much that will help. I guess not. No, just leave it like that. Give me a second. Just leave it as w equals to u squared plus 1. So u squared equals to 1 w minus 1. Therefore, dw equals to 2u du. I still have issue there. It's integral when u equals to 1, this is 2, this is u to the 4th plus 1, this is u to the power of 1/2, this is w minus 1, which I don't like. I don't like this. du equals to dw over 2 dw over 2 u. I don't like this very much. Really, really bad. Now I will just leave it here. The second method, I will use my u equals to secant theta. So du equals to secant theta tangent theta d theta. Okay, so u squared plus 1 will be, oh, I'm sorry, it should be tangent, huh? My bad. Should be tangent. So u equals to tangent theta, the derivative is secant squared theta d theta. Okay, so u equals to 1, so this is pi of 4. This is tangent inverse of e squared. This is secant theta on the top over tangent squared theta times secant squared theta d theta. That is secant theta times tangent squared theta plus 1 over tangent squared theta d theta. That gives us integral from pi over 2 to tangent inverse e squared of secant theta plus 1. So there will be cosine theta over sine squared theta d theta. Integral of secant, we know that's natural log of secant theta plus tangent theta. And if my w equals to sine theta, my dw will be cosine theta theta. So this will be integral dw over uw squared and this will be sine, this is 1, this is sine of tangent inverse of e squared. Do I make any mistake? Why did it change to pi over 2 instead of 4? Let's see, what kind of substitution I did there? Oh, pi over 4, thank you. This should be pi over 4. This should be pi over 4. This should be pi over 4. So this would be, thank you, that's a crucial one. This is from pi of 4 to tangent inverse of e squared. Man, that's kind of heavy. I will do the numbers later on altogether. That's tangent inverse e squared minus, now it becomes plus 1 over W from radical 2 over 2 to tangent inverse of square. Then carry this to very far left. So this is natural log of secant of tangent inverse of E squared plus tangent of tangent inverse of E squared. It should be sine, which I can simplify further on. Yeah, okay, yeah, thanks for, I happen to see that also. So this is minus natural log of secant pi over 4, that's radical 2 plus 1. All of these plus 1 over sine of tangent inverse of E squared, which if I were you, I will compute that a lot earlier, minus 1 over radical 2 over 2. Now the thing is, this one is easy. This is E squared, right? That's E squared. Agree? Okay, our issue is how to simplify this and how to simplify this. Okay, notes, side notes. Let theta equals to tangent inverse of E squared. So tangent theta is E squared. If this is theta, this is E squared, this is 1, this is square root of E squared plus 1. Okay, so secant of tangent inverse will be square root of E squared plus 1, right? Plus E squared minus natural log of square root of 2 plus 1. I can just use parentheses here because that's a positive number. While the sign of that theta will be, this will be square root of E squared plus 1 over E squared plus, I'm sorry, minus square root of. Ugly answer, huh? Ugly answer. Okay, but actually, in the end, it's about the right person to marry instead of the cute person to marry. Right? I mean, it is true in real life. Okay, it's true in real life. If you want to have a good math problem, don't expect a nice solution. Okay, if you want to get a good husband, a good wife, do not expect a cute one. Okay. To be honest with you, if I see this kind of work, this kind of solution, I tend to check my work again, just in case I make any mistakes somewhere a lot earlier. But I don't think I make a mistake. Yeah, I don't think so. I don't think so. You know what? Let me put this together. Simplify a little bit further. This is natural log of square root of E squared plus 1 plus E squared over square root of 2 plus 1. And then plus square root of e squared plus 1 over e squared minus square root of 2. So basically, I put these two natural log together. Okay, I accept the first one, but when you compare with your book, you may see the second one instead. The second method. The second method, actually, let me do it here. Instead of working on the y, let's solve for x instead. Okay, so e to the negative x equals to 1 minus y. So negative x equals to natural log of 1 minus y. So x equals to negative of natural log of 1 minus y. Now, I'm not saying that this will be easier. No, I don't even know if it is doable. What I know is we can try. Okay, now the thing is when x equals to 0, when x equals to 0, e to the negative 0, that's 1, right? So the y will be 0. Okay, when x equals to 2, that's e to the negative 2 equals to 1 minus y. So y equals to 1 minus e to the negative 2. So my y later on will start from 0 up to 1 minus e to the negative 2. Again, I'm not sure if this is a good idea, but let me just try. Dx dy is negative 1 over 1 minus y times the derivative of 1 minus y, that's positive. Dx dy squared will be 1 over 1 minus y being squared. If I add 1 and then put the square root, that's what I have. So the arc length will be integral from 0 to 1 minus e to the negative 2 square root of 1 plus 1 minus y squared over 1 minus y being squared. Now the good thing is, the denominator has cancelled. So this is integral from 0 to 1 minus e to the negative 2 square root of y squared minus 2y plus 2 over 1 minus y. Then I make my u equals to 2y minus, y squared minus 2y plus 2, such that my du is 2y minus 2 dy. That's 2 times y minus 1. Integral of u to the power of 1/2. Ouch. I was expecting a nice thing. It turns out that's not that nice. this will be square root of u minus 1. So this is du over 2 square root of u minus 1 also, or 1 minus a minus 1. This will be integral square root of u over 1/2. Underneath, we have something like this. To change that. Well, anyway, so I have to deal with this later on. I need to deal with this later on. But so far, I don't think I want to go on. You can try to do it on your own from there. Okay, I just try to, this second method basically doing the following. This second method basically doing the following. So imagine if you have a curve that looks like, for example, looks like this. Now, the first method, when you integrate along the x, that's from a to b. Now you change that into integrating along the y from c to d. Who knows that's easier? Who knows that's easier? Okay. Let me see again. I somehow think I may have done some mistake somewhere. I don't know. I just think I just don't think I don't have the solution. That's the thing. So I'm not sure if this I can check this. I would love to know that's correct, but if that's something wrong there, I would like to also know if I did it wrong. Okay. And another thing is I would like to have a more efficient way to do this integration. Okay, I show you three different ways. One of them works, the other two kind of like get stuck. But when you do integration, that's basically what usually happens. Okay. Anyway, before I give you a break, let me take it from here. Let me take it from here. Let me take it from here. I offer you another way to integrate this. Just the integration, not flipping it. I can do the following. I can do the following. I say u equals to 1 plus e to the negative 2x. So the derivative is negative 2 e to the negative 2x dx. Such that, notice that e to the negative 2x equals to u minus 1. So dx is equal to negative du over 2 times u minus 1. With this kind of substitution, I get integral That's u to the power of 1/2 times negative du to u minus 1. And then, of course, I need to change the limit of integration. That will be 2. Let me just do it. This will be 2 here. This will be 1 plus e to the 2. Reverse the order of integration to absorb the negative. Get the 1/2 out, so this is u to the power of 1/2 over u minus 1 du. The thing is, what I did here is basically what I have is here. That's basically what I have. Very similar, not exactly equal to, but very similar. Now the thing is this more integrable compared to the other one? Not sure. Not sure. Maybe w squared equals to w. So dw, sorry, 2w dw equals 2 du. Oh, this is easier. This is easier. Oh, or am I making any mistake? You know what? Right now it's 8:30. Let me give you a break. Let's come back at 8:40. Okay, I did some fix on the mistake I made earlier. Okay, I tried to find my mistake. Instead of just saying, oh, this is, look at the solution manual and see what the solution says, or you go to, what's that? What is the website where you can find the solution again? Start with an S. Well, anyway, instead of finding the solutions from Slader, that's right. Instead of going to Slader and find the solutions, and the results from Slader also come from other students, though, as I know, not necessarily the formal solution from the author. Okay, that's students working together. Sometimes some professor actually also post the solution there. So do not think that the solution from Slater first is always right. Second, that's always the only way to do it. No, that's actually a bad notion. Okay, that's actually a bad notion. Okay, let me give you the suggested homework from this section. Suggested homework will be 8.1, number 3 to number 19. And then I would like to do either number 33 or 35 or 36. Let me do number 36. So number 31, 33, 35. Try those questions. Okay, let me try number 36. Number 36 is the following. The kite's height above the ground from horizontal position, let's say this is the one who fly the kite, okay, and this is the x. Okay. Now the height from the ground is given by y equals to 150 minus 1 over 40 x minus 50 squared. Okay, now that's the trajectory of the kite. Now the question is, find the distance traveled by the kite, as if the kite actually traveled along this path here. Okay, now we want to find the distance traveled by the kite. So y equals to that. So y prime is equal to negative 1 over 20 times x minus 50. When I square it, I get 1 over 400 times x minus 50 squared. So y prime squared plus 1 will be x squared minus, x minus 50 squared plus 400 over 400. I hope you understand. When I add 1, I do the LCD right away. Okay, such that the square root of this guy here equals to 1 over 20 square root of x minus 50 squared plus 400. Then I need to find the distance traveled by the kite. That will be integral from 0 to 80 of 1 over 20 square root of x minus 50 squared plus 400 dx. So this is equal to 1 over 20. Let me do substitution right away. U equals to... No, I don't want to do that way. I will use x minus 50 equals to tangent theta. X minus 50 equals to tangent theta. So dx equals to secant squared theta d theta. It's tangent inverse of negative 50. And this is tangent inverse of 30. What am I doing? I need to put 20 here. I need to put 20 there. Yeah, because of the 400. So that will be tangent inverse of negative 5 over 2. And this is, it's tangent inverse of 3 over 2. This will be 20 secant, and then the dx will be 20 secant squared theta d theta. That is equals to 20 integral tangent inverse of ugly number, negative 2.5 to tangent inverse of 1.5 of secant cube theta d theta. Then from here we do the memorizing. I wonder if you memorize this. This is 20 times. What is the integral of secant cube x dx?
Tangent theta, secant theta.
No, 1/2?
Oh yeah, 1/2
1/2 tangent theta secant theta, and then
plus ln
plus 1/2 ln.
absolute value, secant theta, tangent theta.
So from tangent inverse of negative 2.5 to tangent inverse of 1.5. Let's do the triangle. So if theta, tangent theta is 1.5, so this is 1.5, this is 1, this is square root of 2.25, 3.25. The other one is 2.5, 6.25, that's square root of 7. Okay, so this is 10 times tangent theta, 10 times 1.5. And then secant theta, that's square root of 3 point, I'm sorry, it should be, oh yeah, that's right, 1.5 plus 10 times natural log of square root of 3.25 plus 1.5. Minus 10 times negative 2.5 square root of 7.25 plus 10 times natural log of square root of 7.25 minus 2.5. This is fugly. I don't even know if this is right though. Do you want to check? Okay, that's for 8.1. Let's go on to 8.2. 8.2 surface of revolution. Now the idea is, suppose we have a curve, let's say like this. Okay, in 8.1 we already compute. In 8.1 we already compute the length of this arc here. Now in 8.2 what we will do is we will rotate this, let's say in this case with respect to the x-axis. And want to find out what is the surface of the area resulted. Okay, we want to find the surface area. Now the idea will be as the following. I will do a small cut here. I will do a small cut there. Let me zoom it on the right hand side. Now, earlier, this is our ds, right? Okay, now then I will rotate this. I will rotate this. Now the thing is, what is the area of the resulting, what is the resulting surface? Okay, and the way will be by kind of approximating this surface as the lateral area of a cylinder. Okay, so suppose the height here is y. Suppose the height is y there. That's the radius of that cylinder. Then the area, let me call that this A, dA will be 2 pi y, that's the circumference of the cylinder, multiplied by ds. So the area becomes, the area, if you rotate that, revolve that around x-axis, will be the integral of dA, which is the integral of 2 pi y ds. Notice that this is if you revolve with respect to x-axis, where the y will be the radius to the x-axis. That's the radius of that cylinder to the x-axis. Now in practice, then when we this is the integral from a to b. Now this becomes, I can factor the 2 pi as a coefficient out. The y usually expressed as fx, and the ds will be, oh, you know what, let me just keep it as y. As long as you keep in mind y as a function of x. So this is 1 plus dy dx squared dx. That is if you revolve around the x-axis. What if I go the other way around? I revolve that with respect to the y-axis. So again, let's say this is the curve. This is A, this is B. Okay, and I want to revolve that around the y-axis. Now you grab this section here. You grab this section here. Okay, grab that section there. Okay, this is your y-axis. This is our ds, is it right? This is our ds. Now I will revolve it this way. I will revolve it this way. So what will the radius be? The radius is x. The radius is x. So the area when you revolve, the dA first, this is 2 pi x ds. So the area when you revolve around the y-axis will be integral 2 pi x ds from A to B in terms of x. which this becomes 2 pi integral from a to b x square root of 1 plus dy dx squared dx. Okay, I'm done with this section. It's just about computing it. Am I recording this? Yes. So let's do problems number 6. We have 9x equals to y squared plus 18. And then the x is between 2 to 6. Rotate, find the surface area if the curve is rotated around x-axis. Around x-axis. Now, do not try to memorize too much the formula, but try to learn to build the formula. Okay, so I have this curve. I don't know what it looks like. Okay. Oh, actually, I can find what it looks like. This is something looks like y squared equals. So it actually looks like this, huh? Right? That's what it looks like. Right? Okay, that's what it looks like. And then I want to rotate that around the x-axis. I want to rotate that around the x-axis. When x equals to 2, the y is 0. When x equals to 6, y is what? So y equals to 4. I mean, yeah, y equals to 4. So this is 6. This is 4. Now notice that we actually have 2 ways to integrate this. We have 2 ways to integrate this. The first one, if I see the y as a function of x, so y squared equals to 9x minus 18. So y equals to the square root of 9x minus 18. I will take the positive branch. This is 3 square root of x minus 2. Do the derivative. 3 over 2 times square root of x minus 2 at the bottom. When I square it, and plus 1, that will be, you know what, let me square it first. When I square it, I get 9 over 4 times x minus 2. So when I add 1, that's 9 plus 4 times x minus 2 over 4 times x minus 2. Which is for x plus 3, no, plus 1. over 4x minus 2. The square root, however, therefore, will be 1 over 2 square root of 4x plus 1 over square root of x minus 2. So the surface area is equal to integral from 2 to 6. Is it right? X is from 2 to 6, right? Yeah. Okay. 2 pi. The radius is y. The radius from x-axis is y, but what is y again? 3 times square root of x minus 2. 3 times square root of x minus 2 times the ds, which is 1/2 square root of 4x plus 1 over square root of x minus dx. You need to be patient when you do this, when you set it up. Okay, don't skip steps. See, the reason in 8.1 I keep on questioning myself is because I rush it. I was rushing. So honestly, I don't even know if I get it right. Okay, I don't even know if I get it right. But Thomas, you're supposed to teach us to get it right. No, I'm supposed to teach you how to get it right, but not about getting it right. I just show you the work. Okay, the mean justifies the end, not the end justifies the mean. Simply because you get the right answer doesn't mean you did it right. Okay, I brainstorm you with the show of work. Now come back here. If your setup was not correct, then whatever you do after that is actually a waste of time. This becomes 3 pi integral from 2 to 6 of square root of 4x plus 1 dx. So u equals to, it's kind of boring at this point. Everything after this is technique of integration. So this is 3 pi over 4 integral 9 here, 637 here, u to the power of 1/2 du. Okay, so this is 3 pi over 4 times 2 over 3 u to the power of 3/2 from 9 to 37. So this is pi over 2 times 37 square root of 37 minus 0.7. Okay, I will save this as a note, so don't worry about that for now. Okay, I want to show you the second method. The second method is by seeing this function x as a function of y. By seeing x as a function of y. Okay, so the second way, so let's call this the first way. The second way, the second method, I get 9x equals to y squared plus 18. So x is equals to y squared over 9 plus 2. Notice that that's x as a function of y. So dx dy will be 2y over 9. Dx dy squared will be 4y squared over 81. If I apply the square root, then I get 1 over 9 square root of 4y squared plus 81. Now the surface area equals to integral. You see the x is actually moving. The x is actually moving from 2 to 6. But that curve, when x moves from 2 to 6, implies the y is moving from 0 to 4. Should go up to 6, not 4. Is it right? Let me check my computation. The x is from 2 to 6. Okay, let's check it here. Let's check it here. So x is from 2 to 6. So if your x is 2, what will your y be? Your y will be 0. When your x is 6, that's 54. Oh yeah, that's right. So y goes to 6. So my sketch here, this should be go to 6. Is it okay right now? Okay, so y equals to 6. So the y will be from 0 to 6, 2 pi y times ds, which is 1 over 9, 4y squared plus 81 dy. I will do substitution. U equals to 4y squared plus 81. So du is 8y dy. This is 2 pi over 9. That's 1/8 integral. This is u to the power of 1/2 du. The limit of integration will be when y equals to 0, the u is 81. When y equals to 6, this is 4 times 6 squared plus 81. I'm so lazy. Now then, this is pi over 36 times the integral of u to the 1/2 is 2 over 3 u to the 3/2 from 81 to 4 times 36 plus 81 is what? 225. So this is pi over 54, 225 times 15 minus 81 times 9. Oh wow. Compared to the previous answer, something not right. Yeah, something not right. See, I get 2 different answers right now. But I somehow think I don't make any mistake here, did I? My second method. It's a lot nicer. My first method. Let's see, do I make any mistake? My mistake is here. This is my mistake. It should be 25. So this should be 25 times 5. Okay, let's continue. So this will be 125 minus 27, 98. 98 divided by 2, 49 pi. Do I get 49 pi if I do it that way here? I will just use my calculator. Yeah, I get 49 pi too. Okay. Now I did only one question, but instead of doing a lot of problems, I show you how to attack a problem in 2 different ways. In my opinion, in this case, it's easier for us to attack using dy instead of dx. Okay. Let's summarize a little bit before we do another problem. See, suppose, no, not this one. Suppose this is my coordinate system and this is my curve. Okay, I have from A to B or C to D in Y's. Now take a segment there, take a segment here. This is my DS. Okay, suppose I rotate that with respect to x-axis like what we did earlier. Then the radius will be y, right? The radius will be y. Now, then the surface area now can be expressed in 2 different ways. Surface area is integral from x equals to a to x equals to b of 2 pi y ds. Right? If you use x, that will be integral from a to b 2 pi y square root of 1 plus the square of y prime dx. But if you change your ds in terms of y instead, it becomes integral from from c to d 2 pi, still y. But the y here, you don't need to change into x. The y here has to be a function of x, right? The y here is not a function of x. It is a function of x, but you don't need to change that to x because the integral variable of integration already y. The guy inside here is the one you need to play around. This is 1 plus x prime squared. So there are actually 2 different ways to compute the surface area, just like I showed you earlier. Let's see number 12. Now, I was lucky. I picked a question that I can do both ways. There are times that one of them doesn't work. Number 12. No, I don't want number 12. Let's do number 10. Number 10. Y equals to x cubed over 6 plus 1 over 2x, where the x is between 1/2 to 1. Again, you revolve this around x-axis. What we need is, on your scratch paper, what you need is the surface area is equals to integral from 1/2 to 1, 2 pi y ds. Is it right? Now, the thing is, imagine your ugly, this y is so ugly, and you need to substitute this into the x, in terms of x. That will be so messed up, right? Okay, so you may, in that situation, you may consider converting this in terms of x instead. Okay, but it's give and take though, give and take. We never really know what is the best way until you actually work it out. At least with me right now, I don't know. I can't really tell. Okay, but suppose that's what I need. Let me do y prime the standard way. Y prime equals to x squared over 3 minus 1 over 2x squared. I'm sorry, x squared over 2. So I factor the 1/2 out. It's x squared minus 1 over x squared. If I square it, is 1/4 x squared minus 1 over x squared being squared. When I add 1, that's 1/4 times x to the 4th minus 2 plus 1 over x to the 4th plus 1. I need to plus 1 here, which is equals to 1/4 x to the 4th minus 1/2 plus 1/4 x to the 4th plus 1. That's, I hate doing this routine. But this is equals to, fast forward, this is equal to 1/4 x squared plus 1 over x squared being squared. Okay, such that the square root equals to 1/2 times x squared plus 1 over x squared. So the surface area will be integral from 1/2 to 1, 2 pi y, which is x cubed over 6 plus 1 over 2x times 1/2 x squared plus 1 over x squared dx. Well, it's actually not that bad. The 1/2 with 2 cancels, the pi goes out. This is 1/2 to 1. And what I will do, basically, I need to multiply this with this. I FOIL that, and then later on, I will integrate the polynomial. So that's 1/6x to the 5th plus 1/6x plus 1/2 x plus 1/2 x, 1 over x, 2x cubed dx. And 6x to the 5th, 3, 4, 2/3. That's 2/3 x, 1 over 2x cubed dx. Then integrate that. And x to the 6 over 36 plus x squared over 3 minus 1 over 6x to the negative factor square, or 1/4. It's 1/4. From 1/2 to 1. And you can compute it yourself from there. So it's not that bad actually, huh? It is actually not that bad. Number 14. Number 14, we have the curve y equals to 1 minus x squared. The x is from 0 to 1, rotate around y-axis. I don't remember the formula. I pretend I don't remember the formula. Let's get the curve. Let's say this is my segment. When I rotate around the y-axis, then my radius will be x. Right? My radius will be x. So the surface area will be integral from the boundaries. In this case, my x is from 0 to 1. Two pi x square root of dx dy being squared plus 1 dy. Oh, I'm sorry, dx. What am I doing? My bad. No. This is, yeah, because the variable of integration is x, so this should be dy dx being squared. It's integral from 0 to 1. I pull the 2 pi out. This is x square root of dy dx. That's 4x squared plus 1 dx. Right? That one is easy to integrate. It's u to the power of 1/2 du over 8. Okay, I'm pretty much done with this section. Is there any problem you would like me to do? Oh, actually, that reminds me to do something. Let's try number 26. Let's try number 26. Number 25 is very special geometric interpretation. It has very special geometric interpretation. Number 25. That's kind of strange. Think about this. You try to do it, okay? But basically, here's what happened with that guy called Gabriel's horn. Gabriel's horn is this. That's basically a curve 1 over x, okay, starting from 1 to infinity, that you revolve around the x-axis. Oops. That revolve around the x-axis. Now, something strange happened when we do this computation. What is that, Thomas? You will see that the surface area is divergent. But the volume inside that Gabriel's horn is convergent. In other words, the surface area is infinite, but the volume is finite. The surface area is convergent to infinity, but the volume is finite. As if I'm saying the following, why at first you don't realize how strange it is. As if you have the following situation, as if you have a container, that you can fill with paint. And that container can hold a finite amount of paint. However, that finite amount of paint is not enough to be used to paint this container. If you paint it with green color, you need infinitely big surface to cover the surface of this container. It's like there is no paint will be enough to paint the surface. However, if you fill it up with that paint, the amount of paint you need is finite. Maybe take a look here. Do you see the paradox already? No, not yet. Okay, let me erase it then. The paradox is like this. Imagine if you have that's why it's a very well known question. Suppose you have a container that you fill up with water. Okay, you fill up with water. Okay, now the thing is you can sink in this Gabriel horn. Okay, you can put that in the amount of the horn. Hold on. It says my internet connection is not stable. Can you hear me clearly now? Okay, so the amount of paint in the container is more than enough to fill up the Gabriel's horn with all those paint. However, if you actually use the paint from this box and try to paint the surface, there is not enough paint to paint the surface of this Gabriel horn. Okay. Put it this way. I have a rock star next to me. Energy drink. I have that energy drink. Imagine this figure here. Okay. Suppose I can fill this can with. If I can fill this can with energy drink, then for sure the amount of water, the amount of fluid inside that can is enough to wet the surface of the can. If you take this energy drink out, okay, so you empty the can, then the fluid, the volume of the fluid inside that energy drink will be enough to wet the whole surface. You wet the surface, the lateral, the top, the bottom, right? It should be enough. Now, what this Gabriel's horn doing is actually saying you may have a finite volume, but that amount of paint is not enough to paint your surface. Well, anyway, if you don't get it, try to work it out first and see why it's kind of strange. So basically, it gives you a finite volume but infinite surface. That's right. The inner surface area is infinite also. Basically, you see that surface as one, just one sheet, okay, regardless the inside or outside, okay. But the surface is so big that it is infinity, but it can hold finite number of paint in there. Usually, it's the other way around. Usually you have infinite volume for infinite surface, right? The way we think is this: if you have a container so big such that the surface area is infinite, right? If the surface area is infinite, then the volume should also be infinite. Now we have a case where the volume is finite, but the surface area is infinity. Okay, which is actually strange. Maybe let me make you think a bit more. Okay, so just now I gave you infinite volume and infinite surface. Okay, so it's actually quite easy. Just get a very, very big parabola, a three-dimensional parabola. Okay, the surface must be infinity, right? And it will hold infinite amount of water. Does it make sense? That's for this case. Is it possible then for us to create, is it possible to create the finite surface for infinite volume? Containing infinite volume. It's a bit tricky, but it's actually not hard. Just get a ball. Just get a ball. Is the surface finite? Is the surface finite area? A ball. Yeah, it's 2 pi. It's actually 4 pi r cubed, 4 pi r squared, right? That's the surface area. Now, how about the volume, Thomas? The volume is 4 over 3 pi r cubed. The volume inside 4 over 3 pi r cubed. But the volume outside is infinity. The volume outside is infinity. So this surface, if you see that the other way around, the volume that you look for is the volume outside of this surface. The volume outside of this surface is infinity, right? But the surface is finite. Okay, but the challenge is more into well, can you find a finite volume, but the surface is infinite? That's the challenging part. The way we think is once the volume is finite, as if we are saying, if I reduce that into single dimension, 1 or 2 dimension, it is as if we are saying that if the area is finite, if this region is finite, then the circumference will also finite. We can always bound it. That's the way you think, right? The length of this yellow band here must be finite as long as the area is finite. If the area is finite, then the circumference, the perimeter, must be finite, right? You see, the perimeter is 1-dimensional measure. The area is 2-dimensional measure. If the 2-dimensional is finite, then the 1-dimension is supposed to be finite. That's the way we think. Gabriel's horn is the counterexample for that. You may have 3-dimensional finite, but 2-dimensional infinite. That's why it's strange. I want to do a problem earlier. I forgot. Which problem did I want to do? Number 26. Number 26. Where did I go? Number 26. If the infinite curve is rotated about x-axis, find the area of resulting surface. So we have y equals to e to the negative x. Okay, for x greater equals to 0. By the way, e to the negative x is exponential function, looks like this. Okay, now then I will rotate this. Notice that the length here is infinitely long. The length is infinitely long. But strangely, the surface is finite. It's like the 1-dimensional measure is infinity, but if you see that from 2-dimension, from in 2-dimension point of view, it will be finite, which is strange. Which is very strange. Okay, but let's see how do we do that. I pick one segment. Okay, the radius will be y. Okay, then the radius will be y. Yeah, rotate around x-axis, right? So y prime is negative e to the negative x. Y prime squared is e to the negative 2x at 1. So the ds will be 1 plus the square of y prime. Square root of that, it's 1 plus e to the negative 2x. Okay, and then the surface area will be integral from 0 to infinity. That's the one. 0 to infinity 2 pi y square root of 1 plus e to the negative 2x dx. But I need to change my y right away though. Right? I need to change my y right away. It's a function of x. Let me just put it in. Let me change my y now. This is e to the negative x. This is equals to 2 pi limit t goes to infinity. Remember improper integral from 0 to t. E to the negative x square root of 1 plus e to the negative 2x dx. Let u equals to e to the negative 2x. And sorry, e to the x. E to the negative x. So du equals to negative e to the negative x dx. This is u square root of 1 plus u squared du over negative u. What am I doing? I don't need to do that. This is e to the x dx is this. So that's negative du. Flip the order of integration to absorb the negative. E to the negative u. And then from there, let's see, what should I do? It's 9:50 already. So u equals to tangent theta. So du equals to secant square theta d theta. This is 2 pi limit t goes to infinity integral of tangent inverse e to the negative t. This is pi over 4 secant theta times secant square theta d theta. Secant cube. Integral of secant cube is, I'm kind of rushing because of time. 1/2 secant tangent plus natural log. I factor 1/2 out. Secant theta plus tangent theta from tangent inverse of e to the negative t to pi over 4. Cancel the 2. Secant pi over 4 is radical 2 times 1 plus natural log of radical 2 plus 1. That's the first part. The second part, what happens if the t goes to infinity, so it becomes 0. Theta equals to 0. So secant 0 is 1, and 0 is 0, plus natural log of 1 plus 0, which is basically 0. Okay, now suggested homework from here, 8.2, number 5 to number 15, and then number 25, how about 27? I think that's good enough. That's for today. See you.
Thank you.
Welcome. Good night.